Okay, good afternoon, everybody. Today I'm going to talk to you a little bit about the derivation formula for arctangent. And I'm going to start with a result that's known from calculus. Okay, y'all, this reads the integral of 1 over 1 plus x squared dx. Okay, equals to 1, excuse me, is equal to tangent inverse plus constant of integration. Y'all, another way of looking at this, if you differentiate the right-hand side, the constant becomes 0, and the derivative of tangent inverse of x, or arctangent x, is equal to 1 over 1 plus x squared. Notice that differentiation and integration, what they call inverse operations, by something called the fundamental theorem of calculus. Okay, now it turns out that we can rewrite this in perhaps a more convenient way for a broader set of problems. You can rewrite this as 1 over 1 plus, and y'all, it looks like all we're doing is changing letters, and in form that's all we're doing, but u is actually understood to be any function of x. All right, now let me keep going here. So this is the integral of 1 over 1 plus u squared du. Okay, plus constant of integration. Now this is actually quite a powerful result here. Whoops, hang on just a second, folks. Let me erase that. Okay, I left something out there. Yeah, we can rewrite this. We can rewrite this as, or rewrite this equivalently, or not quite equivalently, but we can rewrite this now. The appearance of this is that it just looks like we're changing letters, and we are in form, but let me just keep going here. This is equal to arctangent of u, or tangent inverse, they're equivalent, plus a constant integration. Now again, just to the naive mind, all we did is change from x to u here. But you see, what this gives you the capacity to solve a broader class of problems. Let me give you an example of what I'm talking about. What if we wish to integrate this result right here? Okay. In this context right here, a is understood to be a constant. A is understood to be a constant. Okay. Now, we already have this result right here. For, if your a was equal to 1, we know this to be true just from calculus 1. Okay, but now we have a squared plus x squared, not just 1. Okay, so how do we manage this? Well, in many cases, just using a little bit of algebra helps you out quite a bit in calculus. So let's see if that can come to fore right here. All right, so what we're going to do here, and this looks kind of unmotivated, but you'll see why I'm doing it in just a moment. What I'm going to do is factor 1 over a squared. Okay, I'm factoring 1 over a squared out of the denominator here. And so what we're going to end up with here would be 1 over, 1, you see 1 times a squared is the a squared that you see right here, right? Then right here you have plus x squared. And y'all, this is not calculus at this point. This is just pure bare bones algebra. Okay, dx. Now you see, you may be asking why all this monkey motion. Well, again, go ahead and see that this is the same thing, right? We took a squared out. A squared times 1 is still a squared. Then right here, x squared over a squared times a squared, okay, is still this x squared because these a squareds cancel, right? Okay. Now, that's starting to look a little more like this form right here, right? Now, let's see what we can do right here with the appropriate substitutions. Let's go ahead and take u to be x over a. Okay. Take u to be x over a. Now, notice right here, a is a constant. That means that du, the derivative of this function of x, du, is equal to dx over a. Okay. Now, this leads to a fairly convenient transformation here. That means this integral is now equal to, okay, what do we got right here, folks? Let's recopy this part right here, folks. Let's work this out a little nicer. This means that a du is equal to dx. Okay. Again, y'all, just real basic algebra right here. Multiply through by a right here, and you get a du is equal to dx. Now you see we're in pretty good shape right here because we can actually rewrite this entire integral in terms of u. See this part right here. Well, I'm sorry, we can rewrite this entire integral right here. Let's just go ahead and write it down. Enough talking here. Okay. All I did was just recopy the constant that was out front of the integrand, right? Now, the integral actually gets transformed into 1 over 1 plus u squared. Okay, y'all see that? Again, u is equal to x over a, so if you square u, you get x squared over a squared. So there's from here to here, right? Now, dx is now equal. That's why they call this a u substitution, folks. It's because you're just substituting a variable u and then rewriting the integrand in a form that's more integrable. All right. So a du is equal to dx, and so this gives us. I'll just write this down. And I could have skipped one step here, but let's keep with the program. Okay. Okay, now let's keep on writing. Y'all notice that this a right here will cancel with one of these a's. And so what you're left with, carry on, okay, is 1 over a out front. And again, y'all, the straightforward algebraic step that occurred, one of these a's cancel with one of these two a's, leaving one of those a's, right? Okay, so you're going to have 1 over a times the integral, okay, times the integral of 1 over 1 plus u squared du. Okay, but you see, we already know what this is equal to. We literally got this form. That, by the way, going from here to here involves the chain rule, where we're replacing x with a function of x. X is just a single variable. U is understood to be some function of x. So in this case, it was fairly simple. U is just x divided by a. That's still another function of x, right? Now, so what is this equal to, folks? According to this result right here, you're going to have 1 over a in front of tangent u. So that's 1 over a tangent inverse of u. Now, I will save the step right here, folks. Tangent inverse of u, but u is just x over a, right? I could show you the step, but I think everybody sees it. It's tangent inverse of u, but u is just equal to x over a. So let me write that down. And I'll envelop that in parentheses just to make it more readable. At least some people think so. Sorry, I'm writing sideways, folks. It's one of my problems, character flaw. All right. So plus constant. Okay. So there you have it, folks. Now this is something you would see. This result right here is something you would see straight in a table of integrals. Okay, you would just see it. You would start. You would start trying to keep track, folks. This equals all the way down to here would be just something that appeared in a table of integrals. But this is the derivation. Okay, let me write this down. This is the derivation of that formula that you could just kind of look up in an encyclopedic way in the table of integrals. Oops. So again, we just derived that for you. All righty, ladies and gentlemen, that's all I have for you. Have a good day here. I'm still experimenting with this, what I'm using here. I'm just looking at something here, folks. Yeah, I would just, this thing does scroll. This is something this is from the Zoom whiteboard. I was just checking to see for future reference if I could scroll around a little bit. All right, y'all have a wonderful day.